Hi, everybody. Welcome back to the Future in Space Hangout, sponsored by the American Astronautical Society. I am really glad that we are back doing these things today, and I think you're really going to like this hangout because one of the things I've learned about I read a lot of polls and I try to understand a lot about what people think NASA should be doing, and all Americans think that NASA should be doing above anything else. It should be doing studying the climate change of the Earth and protecting Earth from potentially hazardous asteroids. Everything else is a distant third, fourth, fifth, sixth, seventh, all the way down, right? So these are the top two things that Americans think NASA should be doing. And today we're going to talk about the second one, protecting us from asteroids. And I'm laughing because you're not going to believe what these guys are going to be doing. Today we're going to be talking about the Double Asteroid Redirection Test, or DART mission, because NASA loves acronyms and DART's a lot easier to say. Double Asteroid Redirection Test. There's a lot in there. So we're going to be talking with members of the team, which is launching later this month, this mission, to help protect us from asteroids. And we're going to find out how they do that and what they're planning on doing, what they're planning on learning from this episode, from this particular mission. But before I bring up my panel, I just want to say real quick, I'm streaming on Twitch, Twitter, YouTube channels, both Deep Astronomy and the American Astronautical Society, and Facebook. So, and I am congregating and aggregating all of the chats from those platforms into one spot. So we hope you will interact with us, leave us questions. And if you're on YouTube, if you use, I think it's :QU, a big red question mark pops up. And I can see it easier if it's a question. So, and I'll bring it up with my panel. So let me bring up my cohorts, my co-guests here. By the way, I want to also thank the American Astronautical Society for bringing these to you. These are, I think, amazing opportunities for the general public to learn what's going on with members of the American Astronautical Society. Okay, so with me today, I've got two members of the DART team here. We tried to have Lena Adams with us, but we had some connection issues because she's busy getting ready for the launch. But with me today is Dipak Srinivasan. He's right next to me, right over there. I don't know. We're doing this now. He's the DART. I'm sorry. He works at Johns Hopkins Applied Physics Lab. At the Civil Space Division. So welcome, Dipak. It's good to have you. Also with me is Andy Rivkin. He's the DART Investigation Team Lead.
Hi.
Hey. Okay. So DART. First of all, this thing's launching soon, right? You guys are getting ready for launch. It's imminent.
That's right. Yeah. That's right. Just a couple weeks from now. Couple nights before Thanksgiving, actually. So the team's gearing up for a very, probably not so relaxing Thanksgiving weekend, but that's certainly an exciting Thanksgiving weekend.
Yeah, is it going from Florida or somewhere else?
We'll be launching out of Vandenberg Space Force Base out in California, actually. And that's actually where Lena is right now. Hopefully she was trying to join us for this call, but we're busy launching a spacecraft and things happen, of course.
Yeah, I'm not going to take it personally. Wish she could be here though. But she is Lena Adams is the DART mission systems engineer, so she could not connect to us here today. So, but we do have everyone else. Okay, so I don't know who wants to give us some background. Should it be Dipak or Andy? Which one of you? Well, and if you want me to bring up the slides or bring up the slides, then just let me know.
Yeah, why don't you go ahead and bring up a slide or two, and we'll talk to that, and I'll give you a little bit of background of who we are and what we're trying to accomplish and why we're trying to accomplish it. And then, if you can go all the way to the beginning of those charts, that'll be helpful. And then, so what'll happen is that I'll talk a little about why we're doing what we're doing, and then Andy's going to jump in and tell you exactly how we're going to accomplish that. So if you can go to the next chart.
Okay.
So just really quickly, I wanted to make sure you all understood who we were. So thank you for that excellent introduction, Tony. So both Andy and I work at the Johns Hopkins Applied Physics Laboratory. So we have roughly 7,500 people working with us, out of which about a little bit more than 1/5 of us work in space, or work on space programs, I should say. We're all terrestrially bound. This chart that you see here is actually a group of all the spacecraft that we've built over the last literally 75 years in doing this. And we've done a whole bunch of different spacecraft. Just a couple of years ago, we launched a very bold mission called Parker Solar Probe, which is actually diving into the sun's atmosphere.
That's great.
Yeah, it's a audacious mission. It's been on the books for decades, and we finally had the technology catch up to enable us to actually pull this mission off, where we're actually diving into the sun's corona, the sun's atmosphere, so we can learn about how our sun works from a vantage point that's never been accessed before. So that was something that we launched just a couple of years ago in 2018, and it's already been diving through the sun's atmosphere, doing repeated flybys. And contrasting that, there's another mission that we launched called New Horizons, which back in 2015 passed by Pluto and right now is continuing its journey through the Kuiper Belt and on its way out of our solar system. So you can tell that we've run the gamut from towards the sun as well as out of the solar system, and you see all these places in between. Can you go to the next chart, Tony?
I can.
But today, what we wanted to talk about is what you see here. This is a iconic photograph that many of you might recognize, some of you might not. So this photograph is actually taken back in 1968, which was historically a very tumultuous year for the United States. There was a lot of things wrong with that year. Martin Luther King was assassinated. There was a lot of civil unrest. We had riots in DC. And it was a very difficult year for Americans and truly around the entire world. But then right at the very tail end of the year, Apollo 8 launched, one of the most iconic missions that NASA's ever done. And as the spacecraft was whizzing around the moon, first time that's ever been done, a fellow engineer and astronaut, William Anders, snapped this picture, which is called Earthrise. First color picture of Earth taken by an astronaut that when it came back to Earth, it really lent a sense of hope and inspiration to everybody around the world. And that's how one of the most tumultuous years in American history closed out, with this symbol of hope and inspiration that, hey, we can do better, we can be better. And I kind of think that, history tends to repeat itself, and we're here right now. It's been a very tumultuous couple of years for a lot of people for a lot of different reasons, right? But one of the things that we can all be proud of, and if you're on this call, you have an interest in space or you work in space, but if you look around the world as well as in our own country, across science and commercial sectors, there has been just a renaissance of activities and just a boom in space, lots of excitement, and something that we can all be proud of. And it's something that I personally am extremely proud of. And again, we're trying to see whether or not space can lend that sense of hope and inspiration that it has been doing, and I think it indeed has. But it's all happening right here on this planet Earth, and it's a planet that we have to work on protecting. Now, space is not a very safe place. There are dangers there, and Tony's T-shirt is one of them. You have the sun. It's not really Pac-Man eating all the planets as indicated on his shirt. But the sun is actually a source of a lot of danger for us. It's constantly spewing out the solar wind, and every once in a while, there's coronal mass ejections where the sun ejects a whole bunch of radiation at our planet, which sometimes could overwhelm some of our spaceborne and ground-based assets. So we have to protect against that. But another thing that's also out in space is, you can hit the next chart, please, Tony, is asteroids. And that's what we're here to talk about today. Now, people talk about, well, asteroids, how often does this happen? Well, this chart is showing a bunch of fireballs where asteroids have actually come and hit Earth or burned up in the atmosphere since 1988. So this is just since 1988, and these are asteroids that are above a certain level. If you include the really small guys that are hitting us nearly every day, this entire chart would be filled. But I'm sorry, I thought I heard a little bit of feedback there. So here, you're seeing that asteroids are hitting us all the time. In fact, I pulled this chart just a few days ago.
I'm going to interrupt you for just a minute. I'm sorry, but Lena just joined, and if I leave this screen, it's going to do this. So I need to do this, and I think that's Elena.
Lena,
that is Elena.
You've rescued me from having to do the engineering part.
Hi.
There
Can you guys hear me?
Now
we can hear you. We can hear you and see you.
Yes.
Wonderful.
Thank you.
All right. This is the first of many wonderful things. Yeah, the first of many wonderful things that the DART mission is going to pull off right now is that we can communicate from California to the East Coast. All right, we got that down now.
Yeah, that's always hard. Okay, this is great.
Right.
Okay, I will turn up some light here.
All right. So,
Thanks, Lena.
just a sec. Let me go back to the minute I move my cursor, it for some reason it goes into that kind of mode. So I have to go and do this. You're looking at my desktop right
That's
now.
okay. We get to see under the hood as to how all the magic happens, right?
That's right. You're looking
So,
at my.
This is the fun. This is the fun stuff.
Okay, there we go. So.
All right. So now we're back to asteroids, and now we have our mission system engineer joining us as well, which is
Yes,
just
Lena
fantastic. Lena Adams. So what I was saying is that asteroids, as I can see in the chat, you guys are kind of surprised. They're hitting us all the time. So I pulled this chart just a few days ago, and the latest one actually hit towards the end of October. It's one of those little circles off the east coast of Somalia. So that burned up in the atmosphere on the last week of October. You know, no harm, no foul, but the point here is that these are happening all the time. Can you go to the next chart?
Okay.
So now we want to find out, and we want to just talk about what kind of danger these things pose. Now this is a big chart, so a whole bunch of words. You don't need to look at the words. What I wanted to, the intent of this is pretty intuitive, right? The bigger the asteroid, that's further to the left or to the right on this chart. The bigger the asteroid, the more damage. The smaller the asteroid, the less damage. That's not a hard concept to understand there. What I wanted to really focus on is actually the bottom part of this chart. So the really large asteroids, the one that can, like the ones that killed all the dinosaurs, made them go extinct. That class of asteroid is so large that there's very few of them that our models say are in the solar system. And we think we've found all of those. We know that we're safe from these, dinosaur killer level asteroids. Now, conversely, on the other end of the chart, we have so many little itty bitty asteroids, but you can see across the bottom, we've found very, very few of them. But that's okay, because those will just burn up in the atmosphere and they're not going to hurt us at all. What we really care about are these asteroids that are in this middle category. These are the ones that can cause kind of regional damage. Like if one were to explode over a populated area or impact a populated area, you would have widespread damage, but local to that area. It wouldn't be civilization ending, but it could cause some serious damage and have very dangerous effects on how we live our lives. Now, across the bottom, you can see that we have not yet identified all of these. So that's why this class of asteroid, roughly 10 to 15 meters up to 100 meters in size, those are the ones that we care about the most. Now, if we go to the next chart, we can see why we care about that. So if you rewind the clock about 50,000 years, we have this crater that was created it was the so-called Meteor Crater about 40 miles east of Flagstaff, Arizona. You can see it caused a crater that's roughly a little bit more than a kilometer wide, but you can see the devastation that it caused. So at the time of impact, like I said, this is 50,000 years ago, so none of us were around. But within a 10-kilometer radius, that's the fireball. What happened as soon as that impact happened, within 10 kilometers, everything is pretty much incinerated. If you go out to 24 kilometers, you have heavy winds, you have heavy damage, and then as you get further and further, the damage gets lesser and lesser. So this is the kind of thing that I'm talking about when I said regional damage. This is pretty bad. So if you go to the next chart, I wanted to superimpose this onto DC. What if this were to happen here? And for those of you that are close to DC, this is what the damage would look like. You can see that DC falls entirely within that fireball area. So it would be completely wiped out. And then a good amount of Maryland and Virginia would also suffer cataclysmic winds and lots of property damage and probably loss of life as well. And just to give you a sense of a scale, that's the tidal basin. If any of you guys have visited the Washington Monument, that's roughly the same size as the crater that was on the previous chart. So you would see a crater roughly that size. Let's go to the next chart.
That area is vaporized?
Everything pretty much everything in the red, you don't want to be there. You're inside that fireball. I mean, there might be some like remnants of buildings that are left over, but that's not a place that
you could look at it this way. I was just talking about this last night with someone. Sorry to bust in. Something 160 meters in size or so, if it hit the Earth, would have the same energy as a 75 megaton nuclear bomb without the radiation. So the largest nuclear weapon ever tested was a 50 megaton one by the Soviets sometime in the 80s, I guess. So this would be 50% worse in terms of the energy expended. So there you go.
Wow.
Yeah, so that's what I was saying. We care about this class of asteroid because we haven't found all of them yet. And as Andy just eloquently described, the damage is substantive. So let's go to the next chart. Next chart talks about what we're doing about this. So back in 2018, the United States government, we put out this plan as to how we wanted to deal with this threat, right? So how does this strategy work? If there was an asteroid that was detected out there, there'd be a multitude of different agencies involved. And this plan kind of binds all those agencies together and talks about, what is NASA responsible for? What is the Air Force at the time, now Space Force and U.S. Space Command? What are they responsible for? What is FEMA responsible for? And that's all collected here. So we do have a plan if this were to happen. Now, the plan has 5 thrust areas. The first goal is detection, tracking, and characterization. We can't really do much about asteroids unless we know where they are. So that's why we have a mission in formulation called the Near Earth Object Surveillance Mission, which is going to hopefully launch later this decade and actually do a survey and try to find all those asteroids that I showed you before that we didn't know about yet. So before we can mitigate these asteroids, we have to find them first. So that's goal 1. Goal 2 talks about modeling and information integration. Here we want to make sure that we understand what the impact scenarios are going to look like. How does the information flow from place to place to figure out the best way of mitigating such a disaster? Goal 3, I'm going to skip over for a second. Goal 4 is the international cooperation aspect of things. So, most asteroids that we know of are blissfully unaware of political boundaries, right? So any kind of asteroid threat is certainly an international issue. So we need to make sure that all of our neighbors that we share this planet with, we're all on the same page and we all understand what each other's roles are and how we communicate information back and forth. So that's what goal 4 is. And goal 5 is actually to exercise all of the protocols that we've defined already. And interestingly enough, that's another thing that we're going to be doing in February of this year, where we're going to be bringing in here at APL, we're going to be bringing in a lot of representatives from agencies such as the Department of State, Space Force, NASA, FEMA, and other relevant agencies, and actually simulate an asteroid strike scenario and test our own protocols to see whether or not we're up for the task. As we all remember over the last year when we had the whole pandemic response, there is a national plan as to how to deal with pandemics, but sometimes things don't go according to plan, right? There's all sorts of new things that creep up, social media, fake news, who knows what. And sometimes even the best protocols that we could think of, we find weaknesses in them. So that's what goal 5 is all about. We have a great plan. Let's stress out that plan and see whether we are indeed prepared. Now I'm going to rewind a little bit back to goal number 3. This is deflection and disruption and mitigation. So if we did find an asteroid that was on the way to hit Earth, what do we do about it? There's a whole series of actions that we could take. And one action that we are testing right now is the deflection method. And if you hit the next slide, DART. And as you said, this is the double asteroid redirection test. And at this point in time, I'm going to hand it off over to Andy, and he's going to dive into what DART is all about.
Okay, hang on just a quick second, because I got a question I need to ask. When you say, this is based on your part, what you just said, when you say that we know where all of them are, when I go back to that slide and I say, we know where 100% of the 10,000
the big ones, the very big ones, we know where they are. Right.
Yeah, and then we only know about 90% of the ones that can cause. I love how you phrased it in the slide. Possible civilization collapse. That one we only know 90%. Well, how do you know what you don't know? How can you say, well, we found them all? How do you?
Well, we have models.
Okay, go ahead.
Yeah. Based on our models of how the solar system forms, we have ideas as to how many asteroids we'd find at different sizes. What should the population be? And it should fall off. We should have a few super large ones, then we should have, a few super large ones, then lots of smaller ones. And these are models that have been tried and true on how the solar system is formed. So these are estimates, right? So when we say 90%, that's not an exact number. We think it's going to be about that based on our own models.
Yeah,
you can also imagine, because maybe this will also help. You can also imagine if you had a jar and you numbered, and you had a whole bunch of marbles in there, and you numbered the marbles, and you pull them out, and you go, okay, this is number 14, and you put it back in, you pull out the next one, here's number 72, and you put it back in, and you keep doing that. Eventually, you're going to pull out the same numbers again and again, and you can use that to say, okay, I can estimate how many marbles could possibly be left because I'm only pulling out new ones very rarely. So that, combined with the kind of models that Dipak's talking about, means that you can kind of mathematically figure out, okay, we don't know the exact number, but we're seeing some of these things often enough and repeatedly and not finding new ones. So we must be pretty close to the end.
Oh, that's interesting. So using your analogy, so we have a jar of marbles, and each one's once you start pulling out, so what you're saying is we are observing a great many asteroids, and we're observing very fewer and fewer new ones
In that size range.
In that size range, and so we can estimate how many we think we've got based on how many new ones we keep observing.
Exactly. We're watching the sky. Yep.
The Dipak is talking about is also giving us some idea of how many should be in there. Because I'm sorry, but if you're wrong by one, it could be a bad day for us. So I just wonder how you got them all. I guess was my.
Yeah, that's a fair question. And after we've been observing long enough that there are only so many places where these can hide, where we would have caught them. Okay. So we feel pretty good.
All right. I'll get back to the slides then. I just wanted to see about that. Okay, go ahead. Who wants to go next? This is where we are now.
Yep. I think I jump in at this point. Okay. So and the questions are great. So I'll try not to dwell on me talking. So this is the DART mission. This is an overview of the mission. It shows the DART spacecraft there. It shows our companion, the Lychee Cube CubeSat, which we're going to deploy something like a week ahead of time, maybe 10 days before arrival. Our arrival at Dimorphous is going to be a rapid one. It's going to be a very, very fast landing, so to speak. We're going to come in at something like 6.5 kilometers a second. You can see the details of the mass for the spacecraft there. We are going to go to a double asteroid system. That's the DA in DART. Dimorphous is the satellite. It's about 160 meters across, which is why we mentioned 160 meters a few times in this talk. And it's orbiting a larger object, the 780 meter Didymus. We know Dimorphous is orbiting Didymus once every 11.92 hours or so. We know that the two of them are separated by only a little over a kilometer from center to center, and less than a kilometer if you go from surface to surface. Once the impact occurs, we're going to make measurements of what happened from the Earth. That's down there in the lower left. All of this is going to occur at 7/100th of an astronomical unit, or a little under 7 million miles from Earth when it occurs. And then that upper right basically has the bullets that's what we're going to do. We're targeting the binary Didymus system. We're going to impact Dimorphous. We're going to change its orbital period, and then we're going to measure what we did from Earth.
Well, you sound very sure that you're going to change the orbital period.
As long as we hit it, physics is physics. If we don't change the orbital period, then someone's going to get a Nobel Prize out of it.
Well, there's something we don't understand about gravity at large scales. So,
so
if you're, I'm kidding.
Yeah. So the next slide there, again, kind of shows.
I'm sorry to do this.
Not at all.
There's an artifact from my screen. I just need to. I have to start from a different spot. There, it's gone now. Okay. Go ahead. Yeah.
So this shows now, instead of coming in from the left, we're kind of coming in from the lower right, but shows the overall situation. We are going to hit Dimorphous. We're going to hit it head on. That takes a little bit of energy out of the orbit of Dimorphous. It drops it into a slightly lower orbit, which is what's shown here. That slightly lower orbit has a different orbit period. We're going to measure the difference. I'll talk about a little more of the details in a slide or two. I believe the next slide should be it is an animation. Whether it's animated or not, I guess, is going to be TBD.
It'll go. There it goes.
Good. So the inner circle there, these are even labeled. There's Earth. The outer one is Didymus, the Didymus system with Dimorphous orbiting it. DART itself is about to launch in this animation. It stays very close to Earth as these things go. It passes outside of Earth, and then everything will arrive in pretty close to the same location in October of 2022. So Didymos is not a threat to Earth. The Didymos's orbit does not intersect that of Earth's. We're not going to do anything to change any of those facts. But Didymos is going to be close to Earth when DART hits it, and so we'll be able to make these measurements.
I paused it here just because things get interesting. So when we're all clumped together like this, and there's not a date, so I guess this is near the collision time.
It's going to be it's going to be next fall. Yeah.
Yeah. Well, you're saying it's not. So Didymos does not cross the path of. Oh, I see it. I can see it in the animation. It does not cross the path of the Earth, so there's not going to be any.
There's no danger. No.
What's the minimum distance it'll get from us?
Something like a little under 7 million miles this time around. It does sometimes get a little closer, but not super close. Not much closer than that. A lot of other asteroids get a lot closer.
Oh yeah, Apophis is going to go underneath the geosynchronous satellites. So
yep, yeah. Apophis is going to come close, and that's also true. This is a two-dimensional depiction of a three-dimensional situation. So that's also true. Is that these planes are not exactly coincident.
That's a great point. Yeah. Okay.
So the next slide kind of shows the scale of these things. Didymos there, of course, on the far right. Dimorphous kind of in the middle. Dimorphous is about the size of one of the pyramids in Egypt. DART is here with its solar panels extended, is a little bit bigger than a bus. DART itself, if you don't count the solar panels, we've been saying about the size of a vending machine. That's not my favorite, and I'm going to give my favorite, even though Lena's going to give me a look. It's also about the size and mass. It's a little smaller than an average cow in size and mass.
I like that unit. At least you're not using tennis courts like they do in JWST.
Everything,
no. Now on, I guess primary mirrors are measured in units of tennis courts. So
yeah,
or at least heat shields are, or sun shields. Okay,
and they're pretty close together. Everything would fit. Basically, if you go to your local airport, a reasonably big airport, but not a super big airport, everything would kind of fit on the scale of an airport. So you could easily walk from Didymos to Dimorphos, just looking for pretzels, probably. So the next slide, and I think I hand it over to Lena shortly.
Oops,
oh no, I'm sorry, back one up. So
hang on.
Yep.
There. Oops. So
you're going the wrong direction.
Sorry. There we go.
That's all good. So, like any mission, there are things that have to be done for NASA to consider us a success. These are the 4 things NASA that DART needs to do for us to be considered a success. We have to impact Dimorphos. That's Lena's department. We have to change the binary orbit period. That's just physics' problem. If we do number 1, we're confident about number 2. We have to measure the period change that is caused. That's now the investigation team's department. And then measure what we call beta and characterize the impact side. So this is basically we're going to hit with some momentum. How does that momentum that gets added to the system get translated into a change in momentum for Dimorphos? And I think that is the next slide, maybe, or maybe
momentum enhancement factor. I'm writing that down so I can ask.
Momentum enhancement factor.
Yeah. That's okay.
So the next slide, this actually shows how we will make the measurements.
I just need to tell you that the little graph at the bottom doesn't animate. I'm sorry, but
all right. So that's cool. So
yeah,
as the moon goes around, you can see that it moves behind the main body. This is Dimorphos moving behind Didymos, and then it'll come out in front. It'll throw a shadow, and then it'll block a little bit of the light of Didymos itself. The bottom trace shows what we would measure from Earth. They're too small, and even though they're close, they're too far away to be seen as more than a single point of light. As this stuff happens, the brightness of that point of light goes up and down, and we can measure the frequency of these the light going up and down. That tells us the orbit period, and then that we measure that before, we measure that after. That tells us what how the period has changed and what DART has done to the system. The next slide then talks about this
there it
this
is.
beta. And basically, if we don't make any debris, if DART hits and that's all that happens, then momentum is conserved and beta, this factor, is 1. If depending on the situation, though, we expect to create debris, we expect DART to throw this debris into space, we expect that to actually increase the momentum change over the original. So this could be an enhancement of a factor of 2, it could be a factor of 4, it could be a factor of like 20%. So we really don't know what this is going to be, and this would certainly affect, if we had to do this for real, if we had to really deflect an asteroid, this would be something we'd want to know. And I think this is where I turn it over to Lena.
Well, hang on. Just again, I'm sorry. I just want to. So, is there going to be something recording this impact from the outside to see the ejecta, or is this going to be something you're going to have to estimate from the force?
The force is strong with us. The force is it binds it. I forget what the force does. It's everywhere.
Well, the force is hopefully going to move this asteroid, but I guess how are you going to know what beta is without whether or not you had ejecta? How are you going to know?
So all of these affect the period change that we measure from Earth. So the larger the beta, the greater the period change,
okay.
which is what we're going to measure. And then there also will be something which I think Lena will talk about. There'll be this cube that I mentioned will be on site.
I'll let Lena go then, because my questions are piling up.
No,
okay,
the questions are good. So.
Okay, yep. Go ahead. Yeah. Oh, Lena.
All right. So can you guys hear me?
I see my alma mater in there. I'm very proud of the University of Colorado for being a
All right. Well, that's important because we have partners all over the world on this mission. So our friendly Planetary Defense officer, Lindley Johnson, always says planetary defense is a global sport. So we're all in it together, and DART is definitely a reflection of it. We built DART here at the Johns Hopkins Applied Physics Lab. I should say here, although I'm at the launch site at Vandenberg Space Force Base, where we're actually launching DART off in less than 2 weeks. So that's here is more global, but we do have partners all over the world. So of course, our launch vehicle is going to be SpaceX launch vehicle. And we have the international partners from the Italian Space Agency that are providing a little CubeSat called Lychee Cube. That's what Andy talked about, something that is actually going to fly by the asteroid about 3 minutes after we impact, and is actually going to take images of the ejecta you were asking earlier. So it's not part of our level 1 requirements. We can figure out beta based on the fact of how much the orbit changed, right? And we're not going to be able to measure the mass of the asteroid just because we will be destroyed once we hit. There are questions on the chat asking, what's going to happen? Is the spacecraft going to be destroyed? The answer is yes. We are the thing that impacts the asteroid. We're moving at 15,000 miles per hour. We are going to be gone. We're going to create a crater that's 10 to 20 meters, or I should also translate into the non-devil units of 6.5 kilometers per second. So let's go to the next slide. So DART is, it's a technology demonstrator. We're not a science mission. It's a very different type of mission that NASA SMD is trying for this time. We are demonstrating a variety of technology. The most important thing that we're demonstrating is the ability to impact an asteroid. And just to give you an idea of how hard that is, you're traveling 107 million miles to hit something that's 0.1 miles in size. So pretty small, hard to see. Most of the asteroids are dark. And we're doing that using an optical telescope called Draco. That's our only main instrument. Shown here, it's based on the Lori instrument. I don't know if you guys saw pictures from the Pluto flyby, where Lori took fantastic shots of Pluto.
Oh, yeah.
Well, so it's a camera based on that that we're using for DART as well. And that's what's going to find the asteroid. And I'll tell you a little bit about how it finds it in a few minutes. But the other big thing that we're demonstrating is the autonomous navigation system, which is what once Draco actually locates the asteroid, that's what actually makes us impact. It guides ourselves in, and the spacecraft becomes completely autonomous. I'll talk about that in a couple of minutes. And all of that is possible in the type of avionics that we're actually flying in the spacecraft. But in addition to that, we're also demonstrating a lot of other technologies for NASA, such as the Nexi ion propulsion engine, which is much more exciting ion engine than previously flown. This one has a lot more throttability, which means you can go visit many more objects. We're not going to be doing that in this case. We're visiting one very particular asteroid, but for future missions, you can go and actually explore many more objects with this engine. We also have a pancake antenna, high gain antenna, called the radial line slot array, and a new type of solar array, which actually rolls out. It was demonstrated early on at NASA on ISS. But we are actually the first mission that's actually flying it, and the first mission that actually is going to have it powered. Before, it was just demonstrating the mechanism of the rolling out. So it is pretty exciting for us. And we have another little baby array on top of the larger solar array that has a bunch of concentrators. And that's really important for future missions that are going to go out to the outer solar system, where you have very little light. And so you want to be able to make use of as much sunlight as possible and concentrate it on your solar cells. So pretty exciting stuff. All right, so let's go to the next slide. So this is our DART spacecraft. It is a box, 2 by 2 by 2.6. And once the roller arrays roll out, we're actually about 18 meters long. So pretty large. The solar arrays are basically flexible blankets that are attached to our spacecraft. What you also see is the Nexi engine on top of the spacecraft, but on the right you see the engine actually undercover because we have to protect it. It has a lot of high voltage stuff, and when it's sitting in the fairing at launch, lots of stuff could rain down on it. Our Draco telescope is inside the main spacecraft and has a cover as well. And then Lychee CubeSat is sitting on the side there. All right, let's go to the next slide. So here's a little light Italian CubeSat for imaging of the asteroids. You know, we all love our acronyms. So Lychee Cube. For a while, we were calling it SelfieSat, which was kind of cool because that's really what it is, right? It's going to take a selfie of us as we slam into the asteroid. Yeah. However, NASA decided to not go with SelfieSat, and here we are with Lychee Cube, but also a good name. So it's a pretty cool little CubeSat. It has 2 cameras, and both of those are going to image us after we hit. And it is actually going to outlive DART because, and you know, it's a really fun CubeSat. Usually with CubeSats, you attach them to your spacecraft and you let them go as soon as possible, right? The moment you launch, you kind of let go. We actually are carrying it at 10 months to the asteroid with us, and are going to let it go about 10 days prior to us impacting. And we're letting it go behind us because if we don't, we don't want to slam into it, and then B, we want to make sure that it's actually flies by after we hit. If we go to the next slide. So after it flies by, it downlinks data for the next 6 months because it has a very small data rate. So, but for us, our biggest thing is really our Draco camera. And you can see it here with the door open, looking out into the world. And it's really basically our eyes to the solar system. And in particular, for searching for the Didymus asteroid and Dimorphous as well. So if we go to the next slide. Because
Hubble had one of those camera covers and they never opened it, or after they opened it once, they never closed it again.
Oh yeah, no, we're not planning to close it. This is a one-time opening cover. The moment it opens, it stays open. This is really to protect us from debris in the launch vehicle, because let's be honest, all the launch vehicle fairings are pretty dirty, and having a sensitive optical instruments where we actually want to make sure it's really clean before we launch, it's important to have a cover. So, so we really are going to be searching for the Didymus system about 30 days prior to our arrival. So that's the first time we're actually going to see it. What we know about Didymus right now, I think somebody asked in the chat earlier, what do we know about the asteroids right now? Well, quite little actually, but also quite a lot. This particular asteroid we've been observing for about 20 years. In 2003, there was a close approach of that asteroid to Earth, and we were able to get some using ground-based radar observations. We were able to at least get a good shape of Didymus, which is the bigger asteroid, right? It's the one that's 780 meters size. And also the investigation team has been doing a fantastic job observing it for the last couple of years and trying for engineers to get us a good understanding of where exactly Dimorphous is in relationship to the larger asteroid. And in particular, looking at all the different light curves of how Dimorphous is passing around Didymus. And also, we have some good ideas. There were some spectral observations of the Didymus as well that give us a good feeling of what kind of asteroid it is. And it's not the most, it's not a metallic asteroid. It is on the chondrite family, which is, I think, and Andy can correct me because sometimes I lie. Andy, it's one of the more common families of the asteroid. And you want to say a couple of more words on that?
Sure, and you don't lie. You sometimes maybe are misspeak, but this particular kind of composition is a very, very common meteorite type. It's the most commonly seen to fall to Earth. So it's very typical of what's out there. It's the same composition that Apophis has. It's the same composition that Eros had and Itokawa had. So it's very common.
Yeah. So, I mean, I think that it's really good for us to be able to hit something that is very common to what we might actually expect in the real planetary defense situation. And I think that's what makes this Didymos binary system such an ideal target. Well, in addition to being extremely safe, because, there's always a question, oh, you're going to hit Dimorphous and you're going to knock it out of the orbit and then it's going to come barreling towards Earth. Well, the answer is no, not really possible. But more to that later. So composition, we know we have a pretty good idea of what Didymus is made out of. But the problem is that we don't really know what Dimorphous is like. Can you go to the next slide? So we only know about Dimorphous very little. We kind of know its size, its basic size. We know how often it rotates about Dimorphous. Thanks to the investigation team, now we know which side it's at what time in its orbital period, because that's really important because we're trying to go hit it when it's farthest away from the main asteroid, because then we can actually see it earlier. And but we don't really know its. And when you're trying to hit something that is dark and you don't know its shape and you don't see it until about 30 minutes before you hit, at that point, an hour out to 30 minutes is the first time where it's actually 1 pixel in front of our camera. It is a pretty hard mission to do. So if we go to the next slide. Yeah, so this is just kind of a little bit of explanation of how we actually target Dimorphous over time. So, 30 days, as I said, we first detected, then about 10 days out, we finally get continuous ground station coverage. So DSN, which is what we're using to talk to the spacecraft, is on with us all the time, together with ES-Track, the European Space Agency dishes. And then last 10 days, we're just performing maneuvers, trying to get ourselves as closely possible, guiding ourselves towards Didymos, which is the main asteroid. And then at 4 hours out before we hit, the spacecraft becomes fully autonomous. The smart nav guiding system completely kicks in. What does that mean? That means that now the spacecraft performs all of the maneuvers itself. It's sending video back to Earth, streaming video basically of Dimorphous. And then we watch paint dry for about 3.5 hours. So if we go to the next slide. So the last hour is when, for the first time, we see the asteroid, hour to 30 minutes, depending on the model that we use. And then really, once we're finally at about 4 minutes out, you can see we're finally starting to see the shape of Dimorphous. And then in 4 minutes, we slam into it. So there's really not much time to react. and we better be right the first time. So if we go to the next slide. So
Okay.
in the last, and you can just let this go. It's going to play automatically. These are some, you
Oh,
have to show some exciting pictures of the spacecraft being built up. It's always really hard to build a spacecraft, but in this case, it was particularly hard because we were doing it during COVID. However, that was, and you have to touch spacecraft in order to be, you can't just be on the Zoom meeting. So we've been coming in for the last year and a half, building up the spacecraft. It's gone through a lot of testing on the ground, doing thermal vacuum. We received our solar arrays. There's Draco being integrated. We tested our spacecraft and were able to shake it because, of course, on the ground, you have to simulate the shaking of the rocket and then what thermal cycles it's going to go through in space, because space is really cold or really hot depending which way you're faced. Lychee Cube got integrated onto the spacecraft. If you go to the next slide, I think the animation probably stalled out, but yeah, so this is our Lychee Cube with our Italian colleagues who visited here. And then if you go to the next slide. Yeah, so you can see the spacecraft actually right before we shipped, all beautiful and ready.
Is spacecraft the only people that use Captan? You see, that's the only place I ever see it.
Yeah, it does look, not all that it shines is gold, I guess, but in this case, the spacecraft is very shiny.
I love it, man. It's the only place I ever see that stuff.
Yep. No, so here's a blanket. So if you go through the next couple of slides, I think maybe the animation is not as
no,
good.
I'm just doing it manually.
Okay, yeah. Just kind of skip through them. You can see we shipped to Vandenberg, and then we arrived at SpaceX recently, where we were basically getting ready for launch. We filled up our spacecraft with hydrazine and mating to the adapter today. Actually, I'm watching it right now. Happen in the clean room. I had to step out for this, but yeah. And then in less than 2 weeks, we're going to go ahead and launch. And then, so if you go to the last slide. Oh, here we go. Does the animation work? Yes, let's do the animation.
Yeah, I'll show you that. You ready to show it? I'm ready.
Oh yeah, let's do it.
All right, I got to do.
You're gonna put the trailer on? All right.
Yeah.
Yeah. So let me.
The trailer is what you will see is what happens right after we launch. So kind of the 10 months in a very short duration of a minute.
Okay, you ready? Here goes.
Yep. And it does make some beautiful music. Shows us deploying, rolling out of the solar arrays. Opens the Draco door. Turning on the Nexi engine.
That's
there
so
you go.
cool, man. Holy
and the tasteful cut at the end, so you don't have to see the carnage.
Oh, the carnage! Come on, this is the exciting part.
That's the best part, man.
No, it's true, but it was a tasteful cut,
Yeah. It was a moment of here it comes to you. Yeah. So theaters next to you next. If we launch on the first day of our launch period, on September 26th next year, we're going to impact.
How confident are you about the launch going off on schedule? The SpaceX guys seem to have this down now. So
they do. They really do. And actually, we're looking pretty good for the first day of the launch period right now. And I want to knock on wood or something because, plastic right around me. Yeah. So, but it's looking pretty good. It actually, they have a saying at Vandenberg which is Vandy doesn't slip. So hopefully most of their launches go off on the first try.
Okay, but here's what I want to know. Have you guys told NASA that you're planning on crashing this thing? I'm kidding.
It is the best job in the world to
course they know.
crash, a $250 million spacecraft. I mean,
Yeah, they love it.
to crash something.
They love it because they know we're not going to come back for an extended mission request.
Oh, that's right.
So they love it.
They're kind of a victim of their own success, aren't they? Every time they do a mission, 5 years. 5 years, nominal.
Exactly.
Nominal, maybe extended to 10
Right.
years.
The rover folks keep coming back 90 days. It's 14 years later. We're
yeah,
not
not to mention the Voyager folks, right? 40 some odd years later.
Yeah.
Are you still asking for money? So, yeah. Well, that's great. So, I, for one, am really glad that this mission is out there because I think the NEO effort that NASA has going, both with NEOWISE and with now with DART, and also there's some Apophis stuff I think that might be planned. That I think all of this is vitally important. Of course, OSIRIS-REx and bringing back some Bennu. So all of this I think is among the most important things that NASA does. And I gotta say the public agrees. I mentioned that at the top of this hangout. The two things that the general public want NASA to do the most is study climate change and study these asteroids. It's funny, human exploration is way down the list. So this is important stuff. Everybody's interested in it. And I guess, is this really, this is a pathfinder for a lot of different technologies. You've already shown us the different things you're going to be testing out on here. Would there be, do you think, based on the however big beta ends up being, would you be doing larger redirect attempts, or is that just too far down the road to think about right now? You just want to get this done.
Andy, do you want to start?
Yeah, so I think in terms of, like one of the slides that Dipak showed near the start, there's this kind of, national strategy, so to speak. And, or not even so to speak, there is a national strategy. And so this is the start of a mitigation test, right? It's testing this out. I could imagine, and I saw one of the questions in the chat, following up, follows a natural follow-up to DART would be saying, okay, instead of hitting something this size of this composition that's a moon, maybe try to hit something that's on its own, something that is metallic, something that's a little bigger. Could we send 2 in a row, successfully? But there are other mitigation techniques that are also under consideration, something like the gravity.
Oh, no, we lost Andy.
He just
all right. So Andy can join.
I can continue his train of thought. So there could be other things that one can think of, different mitigation strategies. And in fact,
sorry, maybe that was good. That was the universe cutting me off. Something like the gravity tractor, which we didn't talk about. There are other techniques, that could be tried. Back to you, Lena.
No. I was going to say there are other techniques, right, that could be tried, and smart people in Planetary Defense have thought of a lot of different techniques that people are trying to figure out a way of testing them. And also just, it depends on the size of an asteroid. There are different techniques that would actually be more applicable. For really small asteroids, maybe a FEMA effort would actually be more applicable than trying to get a mission into flight and try to actually divert it, because it would be really hard to find. And then for larger asteroids, you need so much mass in order to, and depending where it is in the orbit, you need so much mass and how much change in the orbit you can create. You might want something that's a little bit different, either like laser ablation. I mean, that technique has been talked about. Nuclear, where you detonate a nuclear weapon, not at the asteroid like in Armageddon, because that's crazy. But because you have other pieces of chunks of the asteroid that are still going to continue towards Earth, right? What people have talked about setting up an explosion, a controlled explosion that's actually nearby the asteroid, and the shock wave from the explosion would actually move it out of its way. So there are different techniques that people are thinking about, but I think that kinetic impact is just one of them. And go ahead, Dipak.
Yeah, so these are all different techniques. Now, the way that these missions will get selected, because I think the question was, what is next? And one of the missions that's on the books for being next is actually the Near Earth Object Surveillance mission. And we talked about those 5 different points. What Lena and Andy have been talking about is that middle point. Goal number 3 is deflection and disruption. But there's the detection side of things. So we want to launch this surveillance mission so we could actually find all those asteroids that we don't know about. then the question is, well, what happens next and what happens next? There's actually a process called the decadal survey that NASA follows. Yeah, when it's not, so these missions aren't like a bunch of rogue scientists saying it's like, hey, wouldn't it be cool if we did this? And let's spend a whole lot of money there. No, it's actually a very yeah, right. It's not like Hunger Games for money to build the satellites. There's a process that we get the community together and we decide collectively, what is the right place to put all of our money. And once the community sets that course, the scientific community sets that course, NASA will try to appropriate funds as appropriate to make those happen.
However, DART did not come about that way, nor did NEOSM, which is the second planetary defense mission. So this is the first time that planetary defense is actually in the decadal survey.
In the decadal, right. So for going forward, there's going to be a more formal process.
Exactly.
A reflection not only of what scientists want, but the people too. So this is, I think it dovetailed nicely with the decadal survey.
Yeah, I'll also say just real quick that it's I think we, as noted, planetary defense is an international issue, and Didymus itself will be visited by a European spacecraft a couple of years after DART. The Hera mission has been approved by the European Space Agency. It's going to fly. It's going to come and kind of do the assessment afterwards, the after action assessment, and say, okay, how big of a crater was made, make some measurements that DART cannot make. So that is a definite direct follow-up to DART that our colleagues in Europe are going to be carrying out.
Okay.
Yeah.
Well, I want to get to some questions because we're running out of time and I haven't gotten to very many. This is from Hans Milling. So is the spacecraft going to be swallowed or will it fly right through?
Most likely swallowed. At least all of our models so far predict that it's going to be swallowed, unless that asteroid, is completely sand.
Well, you can imagine. I mean, you can stand on a pile of sand or a pile of gravel. The spacecraft is only a few hundred kilograms, and as long as it encounters more than its mass on the way through, it's going to be stopped. And these rocks are much more massive than the spacecraft.
Okay. And Dan from Canada is asking, is there a variation in speed among asteroids as they approach Earth? They all seem to be moving very fast.
Yeah, there's if you're in an orbit around the sun, then there's kind of a minimum speed you're going to have when you're at 1 AU, and it's about 20 to 30 kilometers a second. So there's a little bit of variation, but there's that. And then the Earth's gravity also makes it so that there's a minimum speed that things hit the Earth with, which is the same as the escape speed, actually. It's just going in the other direction.
So it goes from fast to really fast is the answer.
Yeah. AB wants to know if we're going to harvest asteroids. Well, DART's not, but what do you think about that question for the future?
I keep taking all these. I don't know if anyone else has an opinion.
No, there's always there are all the companies out there that are talking about harvesting asteroids, and there are definitely a lot of materials, but it's very hard. It's very hard to make it cheap to go into space, and sometimes it's actually just not worth it economically. Imagine your launch costs you $50 million, so you have to harvest a lot in order to be able to make up for that.
Make it worthwhile. So I think that'll all start off on the moon first. Once we start with Artemis and this whole lunar exploration thing that we have going on, which is another one of the great things that's been going on since the pandemic started. We've been accelerating actually through that. The whole aspect of in situ resource utilization. If we're going to be building stuff on the moon, we need to use resources from the moon because we can't, as Lena was saying, it's cost prohibitive to just launch everything there. So I think it'll start at that point, and then maybe the space mining industry will grow.
Mm-hmm.
We'll see.
It's inevitable. We're going to exploit. No way. So here's from Hans again. What's the latency in the video signal?
About 38 seconds.
Okay. Let's see.
About 38 seconds. It's a very precise number.
I know. Yeah.
Travels at the speed of light. So
John Suffel is giving us some background here. Didymos is the Greek word for twin, and Dimorphous is Greek for having two forms. Some of those scientists are brainy. You guys know what you're doing.
We can be poetic at times.
Well, actually, I want to give credit for our amazing team because for a long time, engineers called it Didymus A and Didymus B. So Dimorphous is a very new name to us about a year ago, right? And that was a really beautiful suggestion to have it called Dimorphous.
How fortuitous is that that we're doing this on how many of these kind of systems do you think are out there? These sort of binary one gravitationally bound asteroids.
Yeah. About 10 to 15% of asteroids, we think, in that size range are binaries. But the trick for DART was that it had to be aligned in a way that it was moving in front of it and back, so you could make the measurements from the ground. If it was kind of oriented like this, then that would be no good. Plus, the moon had to be small enough that you could move it with something the size of DART. Plus, it had to be coming by the Earth in a time frame that we could make the measurements. So Didymus was really the only choice for this mission.
Yeah. Well, you'll be surprised to learn that God watches this, and why he doesn't already know the answer to this question, I don't know. But he goes, I know I'm referring back to the start of the talk, but why are we just thinking about near-Earth objects? What about if one of the Oort cloud has been kicked in? Could we see it, let alone nudge it? You think God would know this, but I'll let you go.
Yeah. So again, I feel like I'm kind of monopolizing here. I do have an answer, but if either of you two want to,
you want to go?
No, actually, I need to drop off for another activity in the clean room. So I'm going to head out, and so Andy can really monopolize it now.
Lena, thank you for taking time out to be here. Godspeed. I hope everything goes well on the launch later this month. Thank you.
See you guys.
Thanks, Lena. Glad you could join us.
Yes. Thank you.
So the studies. Yeah, the studies that looked at the danger to humanity of asteroid impact, did it in like an actuarial way of, statistically looking at this is the number of deaths per year caused by this over such and such period of time. And near-Earth asteroids were the bulk of the danger. And in fact, that's kind of been what set these different size ranges for the searches. So once we find 90% of the 140-meter objects or larger, that will retire a whole bunch of risk. And then it does become the Oort cloud objects that are going to be the most dangerous remaining unknown objects. Whether that leads to a search for those or not, those are really hard to look for, but that is the reason.
I know I want to respect your time, and I'm going to let you go. I'm going to close out with serial port. How long will you be monitoring the expected change in orbit? The period, I guess, of the orbit around of Didymus. How long after you've flown past it?
Yeah, well, Didymus will be easily observable. Will be observable from the ground-based telescopes through spring of 2023. I'm sure we'll be looking at it through then. Then it won't be observable for another couple of years. So I'm sure we'll look back when we get the chance, and then Herald will show up. So kind of the immediate plans are through spring of 2023, and then we take a break.
Okay. Well, Dipak Srinivasan and Andy Rivkin, thank you guys for taking time out. Also, Lena Adams, she was also here with us. Thank you guys for taking time out to talk with us about the DART mission. I'm excited. I'm sure we're going to be all checking out the launch and the telemetry as it comes in. Will you guys be reporting next year as it approaches, kind of like what they did with Osiris Rex, or is it going to be an after the fact kind of thing that we learn about? You know how when they were going towards Bennu, we kind of got updates relatively quickly after they occurred. Is that going to be something you're planning for, or will it be much later?
Yeah, it'll be an event. You'll see a lot of build up leading up to this, leading up to the the eventual impact. And you can follow us on dart.jhuapl.edu. I think there briefly flew up on the screen. So there'll be updates constantly posted on there. Plus there'll be hopefully a greater amount of events such as this. Tony,
yes.
we'd love to be back here and and that build up to the impact. It'll be great.
Yes, so, let's do that. I'm ready. I am ready.
We'll
Anything you want to do, I'll make myself available. So I would love to help you guys and talk about this some more. So let's.
No, it's great that your program and just in general getting the public involved, and we just want this to touch everybody. It's an exciting mission. I encourage everybody to check out the website, dart.jhuapl.edu. There's actually a little quiz on there called Planetary Defender. We can see whether or not you guys are paying attention to this talk, and you can earn a badge to be a planetary. Join us as planetary defenders. I encourage you all to do that.
So there's
And,
a qualification involved. Okay.
That's right. That's right. It's actually a test of us. Did we do our job well enough to inform you guys so you can pass the test? Right. So we'll see.
All right. Well, thank you guys so much. All right. Well, so on behalf of my guests, I want to thank you, and I want to thank the American Astronautical Society. Thank you for making these possible. Please check them out, the American Astronautical Society, and consider becoming a member because they do some important work, and their members are out doing exciting stuff like this. So just want to astronautical.org is their website. So thank you. Guys, for helping make this possible. So I guess I'll see you guys on Tuesday where we'll be talking more about the decadal survey. And thank you so much for watching. And as always, keep looking up.